deal. Oh, there's another watermelon. I feel better.
I have a backup one.
Okay.
You don't like that? I have another one. I have like a serred one.
No, it's fine.
Okay.
And
Oh, and we need some tape actually. Here's the thing about doing it with the watermelons, it tends to fall apart.
Is that what he said?
So
I think that's.
what I'm going to do is
oh, it's clever.
tape it together here,
Six.
so that it won't
Then
actually
you
fall
only have
apart.
one cut.
No parallel. How's the juice dripping? Do you need a towel right there?
Actually,
Oh, should I
It's
just
not
cut
cut all the way
through?
through,
I was
yeah.
trying to not cut.
oh, you want to not? Oh, that's fine.
But
As long as we'll be able to recognize that they're different pieces, that's fine. Okay. All right. Cut number
that was
one.
one.
Ta-da.
Number two. Oops. Sorry.
Oh, clever.
Okay. Cut number two. So is everyone in agreement on how many pieces we should have now?
Yeah.
Yeah.
How many? Yeah.
Dan, you're doing a great job. Thanks, Alex. Three.
Okay. And now it's
Okay.
a hard cut. I
So-
won't make you do five.
I don't want that. I don't want that. I want this. Okay. Please.
Okay.
Separate them out.
Now let's see. And this we have got one, two, three.
Some of them you just have to break them. because
Oh, yeah, I
you
have
cut all
both.
the way through.
You can just finish the cut. One.
One.
Two.
Two. Three. It's like these pieces are taped together. Four. Five. 6, 7.
That's 7 right now.
That's
Yeah.
seven so
So
far.
here's the big X factor.
8. 9, 10. Yeah, sorry. 11, 12, 11,
Wait a
12,
second.
13, 14.
This piece came jumping out. Did that come from
It was
somewhere?
off of this one.
Oh, okay. Did you
That's
guys
not
see that?
bad.
So this is bad. I think I made the wrong cut because this looks like an octant and this looks like an octant. And I just missed that octant. I think it was like that.
Oh, I see what you're saying.
So there should, yeah, there's, so if
None of
maybe
these.
your
Almost a
plane was
little
just
piece
a
on
little
there.
bit,
Yeah, I just did it a little bit
too
off.
symmetric or
Right.
something.
Right there, that's it.
Actually,
Actually, you've got a really
Right here.
tiny one.
Aha, we found it. Like a very small piece
I'm
of
not
wire.
Just
convinced.
missed.
Okay,
I am
so,
not
so,
convinced.
so this is somewhat persuasive, I think. It'd be
Well,
nice to try another one.
It's a good lower bound.
It would be nice to think about this some more and try to understand what's going on. Dave points out that assuming that this really was 15 with that little one, that's a lower bound. Can we get more than 15?
I think 16 is a theoretical upper bound.
Okay, explain why.
because you can do no more, you know better than double each time. Because each individual piece can only be separated into two pieces.
Okay, great. So in fact, if we were allowed to rearrange pieces, then how many could we get? 16.
Why?
Each time you cut, you could just rearrange the pieces, karate chop through, so you get 2 pieces and 4 pieces. Each time just arrange them in line and do a big karate chop and get 16. Can we get 16 though without rearranging the pieces? Is there some way to get even better with our second watermelon? What do
And
people think?
why can't you cut a piece into 3 with 1 cut?
You have to have a pretty straight knife.
Or
Because it's a
pretty straight
straight cut.
piece.
Or
It
pretty
has to be
straight piece.
it has to be concave for it to be able to cut into
Oh yeah, or a pretty
Yeah,
straight
kind
piece,
of.
right.
Yeah, so there are some shapes that you could cut into 3 pieces. What would be an example of a shape that you could cut into 3 pieces with 1 cut?
Like a S,
Boomerang.
solid S.
Like a
Yeah.
kidney shape or an S shape. There you could cut into quite a few pieces, for example, or maybe more.
But we
Okay.
said straight cuts. Well, that's
But-
a straight cut.
Yeah,
To
okay,
get
but
the
the convexity of it, convexity means that any 2 points, so this is not convex because there are 2 points in here, and the straight line connecting them does not live inside the shape, so to be convex. Any 2 points, the straight line between us within the shape, so, yeah, because of the convexity, you can only get 2 pieces. Okay, so 16 we could do if we rearrange. What do people think about 16 without rearranging pieces?
I realized I messed up the cut.
Why?
I was looking at I was trying to tilt the watermelon so the entry point would be not perpendicular to any axis.
Mhm.
But then once I found it, I put the watermelon on the table and I cut through the middle of it.
So by cutting through the middle, or almost the middle, that's why you got such a teeny tiny little cut. So cutting perhaps not quite so far through the middle. Okay, let me get the Play-Doh to save for
I think there's an
later.
orthogonality concept at stake here.
Could you explain, Mark?
Yeah, like when you do this, and then this, you're getting right angles, right?
I'm sorry.
And then like, and you're getting like a third axis and you go like this. And so basically, we know in 3 space you can have 3 axes at right angles to each other. And when you get into the 4th cut, then it gets problematic to get a cut that's orthogonal to your previous cuts.
So if you weren't convinced by the watermelon that we can get 15, you can see it. I'll show you quickly a picture that has the same sort of idea. Let me get it quickly. Thanks.
part.
Who wants an extra towel? I brought 2, yeah, in case.
I think she's okay.
Okay.
Feel free to help yourself to watermelon now or later.
Now, that's right.
Yeah?
Got some plates.
Oh, you can take it.
Plates and napkins.
We might want to recut some of the pieces so that somebody doesn't end up with an octant of watermelon.
Well, I think Danny should get the octane because he's the
Oh, I'll get it on the next one.
Yeah, they don't. Juicy.
California watermelon?
Probably so.
Do they grow pretty much everything in California?
Well, there's some things we can't grow because this is.
Y'all think you're so cool.
You
It's
got
not cold enough. We
amazing.
can't grow like
Cranberries.
pain and
You
stuff.
can't grow bananas. We don't do.
Yeah,
cherry
bananas we
You don't
can
grow
blueberries.
depression.
We don't grow depression or sorrow here.
You can get blueberries.
They
in
don't
the
grow
mountains.
here. There's a banana orchard down past Santa Barbara, but they don't actually grow.
We go camping in the summer months
Oh.
in our daughter. This place where there's like 22 waterfalls and this one like down off of the mountainside thing. And on the way there, there's this awesome blueberry grove where this old couple owns it and clearly doesn't want to earn a profit off of it because people pick their blueberries and then go and sell them like down the street, like on the street. And they don't care. They know it. No, that's fine.
Get this for Joe.
They're so good.
Josh,
So
oh, is
nice.
that her?
Dave, do you know how to project this?
I can guess.
Oh.
I wore the right color shirt today. Thank you.
Thanks.
No, wait.
Got that, okay.
Thank you.
Quack on his wings for you. We saved it for you.
There we go. Okay. This is just the Mac Grapher program, which I like a lot. I didn't draw a watermelon in here, so you can just imagine the watermelon's really big, and these are the cutting planes. So here's the first slice, here's the second slice, here's the third slice, and now I think what Danny was doing was something pretty much like this.
That's a fun use of grabber.
Okay, let me,
So you went through the center.
yeah, he went pretty much to the center, but if we push it off a little bit, so we're going through the center, it looks like sort of on top of the pink, we're gonna have, well, we had the original 8 quadrants, and then we end up on the top of the pink, we're dividing 3 of those quadrants, and then on the bottom of the pink, we're dividing 3 more quadrants, so that would make a total of 6 divisions, 6 additional pieces, or 14 slices. But if we move the plane a little bit off the center here, then we're getting that tiny little piece with no skin around it right here. So that's that extra 15th piece that we're actually slicing. Okay. Okay. So hopefully that's fairly convincing that we can get these 15 pieces. But that's just the tip of the iceberg here. Now we need to really understand what's going on and see if Danny's conjecture about 26 is correct. Okay. So. Okay. So working with, I love working with 3-dimensional things. I love the visualization, but it's really, really hard. So how can we make this problem easier? I think Danny already suggested one way he was thinking about it. Okay, so let's go a dimension down to 2 dimensions. Actually, let's go even make it even simpler. Instead of, so the 2-dimensional problem would be what? What's the 2-dimensional problem if we go down 1 dimension? Okay, how many pieces can we slice a plane into, or a pizza into, or a pancake into? I think some of you all might have done that problem last year with Sue Van Hatten. Is that right? Slicing a pancake into pieces? Okay, but let's go down 1 more dimension. So going 1 more down dimension, what can we slice into pieces? A wine, or licorice stick. So how many pieces can we slice a licorice stick into? Okay, and because we're not allowed to rearrange between pieces. So with 4 cuts, we're just going to do 1, 2, 3, 4 is what would be here, and we get 5 pieces. Okay, so in general, so if n is the number of cuts, and I'll say ln is the maximum number of pieces of licorice, we get
One.
1, and so on. 1 cut we get 2, 3, 4, 5, 6. And in general, for end cuts of the licorice, how many pieces does the licorice split into? And plus 1. Okay, great. So the licorice problem is not hard, right? Okay, so let's go on to the next dimension, which is the pizza. And I'll call that P of N. For pizza or pancake. And take a moment and see if you can figure out how to fill in the rest of that chart, or maybe you might remember it from thinking about it last year. I didn't bring any pizzas, but unfortunately it's pretty easy to draw them. Or as people were pointing out, we don't really need the pizza, we can just draw lines in the middle. Wow, I see lots of good answers here. All right. What's your name?
My name is Lisa.
Lisa. Okay. Do you want to start us out like with the first few here?
Okay, well, let's see. At n equals 0, I think we're looking at one entire pizza.
Yeah, I can
still.
agree with that.
Okay, I ran a line through and miraculously ended up with 2 pieces.
Okay.
So I think we're still on board here. Okay, then, let's see. Third cut, I got 4 pieces.
Okay.
On the 4th cut, I think I managed 7.
Okay, you want to come draw your 7 pieces up?
Okay, try that. Okay, so this is my pizza.
That's a pizza.
Yeah, then I came kind of this way.
Okay. Great. Okay, and what do people get for the 4th cut? So here an 11?
Yeah, I got it.
Okay. Anyone else want to come show the 11th?
Let me go ahead and put somebody else.
Okay. Great. I'm sorry. Okay. 11. Okay. Is it possible to get, so if I had the 7 to start with, does it matter where I put the 4th cut there?
Yes. You shouldn't go through the intersection of any 2 lines.
Okay, so if I moved it, it's sort of like the same problem we're having with the watermelon, so that it's not really, right now it's sort of in a random position in a way compared to the other lines, but if I moved it so that it actually shared an intersection point, then I'd have less pieces. Okay. Anyone get the next one? So, why do we get these numbers? And do you notice anything, any relationship between the licorice numbers and the pizza numbers here?
Pizza numbers are
The licorice numbers
the
are.
previous licorice number added to the previous pizza number.
Okay, so the pizza number is the previous licorice added to the previous pizza. Okay, so in other words, I have that P of n is the previous pizza number, P of n minus 1 plus the previous licorice number here. Okay, so given that relationship, what should then be on the next line here? What should this number be here? Without having to draw it, thank God. Okay, 22. Just adding these 2 numbers together. Okay, so why is that true? What does this pizza problem have to do with the licorice problem? Why, when we add another line, if we do it right, if we're lucky, or why should we get, let's say, when y is P of 5 equal to P of 4 plus L of 4. Y is P of n. Let me just get back up a little bit to where we were. And we had 4 lines.
it's cut 4 times.
It's like I'm putting, I don't have long enough licorice, but it's putting in a licorice stick. These previous 4 lines are cutting that licorice stick with 4 cuts and getting 5 segments of licorice. Let me draw the licorice here. Okay, so this licorice here is getting cut by the previous cut lines into L of 4 pieces, right? 4 cut lines cut licorice into L of 4, which is 5 pieces. Okay? And what about those 5 segments?
I mean, each one corresponds to a 2-dimensional region above it. Which is
Okay.
down.
Each of those licorice segments is splitting a piece of pizza in 2. So each of those licorice segments gives us an additional slice of pizza. People agree with that? Okay. What if I had started off badly and just cut my pizza sort of the traditional way? And then I wanted to do one more cut and get the most pieces I could. How many pieces could? Right now I have only 1, 2, 3, 4. I have 4 cut lines, and I have only 1, 2, 3, 4, 5, 6, 7, 8 instead of 11 pieces. How many additional pieces could I get with another cut line now?
It looks like you
5
might only
more.
get 4 more because you can't. I don't see a way to get 5.
You can cross 4 lines, you get 5 pieces.
Okay, yeah, you're right, I see.
So as long as I can cross 4 lines,
Okay.
it's back to the licorice problem and I'm getting 5 pieces. So that's sort of the key thing. Okay. All right. So we don't have a formula yet for a nice little formula here. We may not get there, but I'll give you a handout and we can work on it tonight. But we have an understanding for how to generate the numbers. Let's see if we can carry that kind of reasoning through.
I think I have a formula, but I don't know why I'm like double checking. Maybe I'm checking too fast. Just make this work. But should I
I'm
write
gonna give
it?
it again. So you can tell me what to write it up.
1/2 n squared minus 1/2 n plus 1.
Like that?
Yeah.
Works for 1. It's looking good so far. I think this is the right formula. Did anyone else get? People agree this works?
Well, it is a quadratic, what you have so far.
I got plus 1/2.
Is it plus 1/2? Yeah, actually I think it is.
That's what's something I
Hang on.
like. It's not working that way. I know that's like right around the right idea.
I don't see that
Well,
working on 6.
There is a standard way to find the quadratic formula using finite differences. So you don't have to think that hard.
Right, so the differences here are, well, the differences are the licorice numbers. And the differences here are linear.
Alright.
So these should follow a quadratic function.
Right.
So they
That's
should
why I
follow
found
something
just using basic.
of this
These
form.
systems of equation.
Yeah.
It should be something of that form. And if we plug
You
in,
mean n, not n squared.
yes, if we plug in these numbers, we ought to be able to solve for A, B, and C.
Right.
Which is probably what you did.
That formula is correct.
I'm just checking, is that correct?
Is it
I think so.
I don't know. I mean,
If you plug in 1,
Plug in n equals 1.
doesn't work.
There's a quick way to do it with Pascal's Triangle.
We'll get there, I hope.
Okay.
Okay, wait, let me just check and make sure this is, see if this is right or wrong.
Huh?
when you plug in n equals 1, it's
We'll
not
get there. If
work.
we don't, he'll get there. It doesn't work.
half of 1 is half.
Oh, I
Minus
see, yes,
half of 1 is half.
But it's
Plus
supposed
0.
isn't
Plus
it supposed to
one.
be plus?
Oh, when plug in 0, oh, you're right, it doesn't work for 1.
Yeah.
Okay, let's try, I think it might be this one.
Yeah.
Does that work better?
Half of 4 is 2.
Yeah. And let's try
What?
the next one for 16.
I wonder
I'm
where I
pretty sure
got
this is
my
right.
plus,
8,
my minus.
Yeah, because it's one
Yeah.
more than, yeah,
This should work. Okay.
one more than triangle.
So let's take our understanding of how to generate the pizza numbers sort of recursively and see if we can use it on the watermelon numbers. So we started with the watermelon numbers. Certainly we're pretty sure of the first few. This is the maximum number of pieces of watermelon. Okay, so with 0 cuts we have 1, with 1 cut we have 2, with 2 cuts we have 4, with 3 cuts we had 8, and with 4 cuts we could get 16. We haven't really proved that we couldn't, I mean we get 15. We haven't proved that we couldn't get 16, but and Danny's conjecture was 26 here. So can we use the same sort of reasoning to understand the watermelon problem here? Yes. How? What should the
It
next,
looks like
does Danny's conjecture look right? What should the next
Yeah.
number be?
42
How'd you get that?
out of 16.
Okay.
I did.
So you're doing the
I
same.
add W of n plus p of n.
W of n minus 1.
Oh, right, we're backing it up.
So we're using the same kind of relationship. W of n is the previous number of watermelon slices plus you're adding the previous number of pizza slices. Okay, so this is the sort of the conjecture. Let's see if we can convince ourselves that this is really true. Why should W of 4, why should that equal W of 3 plus pizza of 3? So when we do that 4th slice, why are we adding pizza of 3 extra pieces?
This is sort of the similar analogy between the licorice stick and the plane, and now we're running a plane through a three-dimensional object in the same sort of a manner.
Okay, so our 4th cut, this is like my 4th cutting plane, say. It's going through the watermelon, and where's the pizza of 3 come in?
That is the pizza.
Okay, so this is the pizza, and those 3 previous cut planes, how do they intersect this cut plane? How do 2 planes intersect?
In a line.
In a line. So those 3 previous cut planes are etching 3 lines on this new cut plane. And those 3 lines divide our plane into pizza of 3, or 7 pieces. So those 3 lines etched in here divide my plane into 7 pieces, which means how many new pieces of watermelon should I get if I do things right? How many? So, yeah, P of 3, or 7 new pieces, because each one of those regions of my that my plane is cut into corresponds to dividing a piece of watermelon in half. So this really hard problem, we can actually now generate all the numbers we want for the watermelon and have an understanding of where they come from this lower dimensional problem, which I think is really cool.
It's definitely helpful if you're trying to serve a lot of people with one ornament.
and your knife is so old that it's only going to stand a few cuts, and you've got lots of duct tape. So yeah. So where can we go from here?
Let's come up with the formula.
Okay, we could. There's lots of places we could go. We could try to come up with a formula. Where else could we go? How can we generalize this?
So 4-dimensional watermelon, or
Great, four-dimensional, so we,
Something.
yeah, four-dimensional something. I mean, with the watermelon's not really necessary. You can sort of convince yourself that the same problem with dividing the watermelon is just like how many regions can you divide space into with planes. So you can think about that and convince yourself it's the same problem. Just, you know, one way to think about it is it's a really big watermelon, right? It sort of takes up all space. Okay, so yeah, so you could do a four-dimensional analogy. So, you know, call this like hyperspace, which is the number of pieces, the maximum number of pieces of four-dimensional hyperspace you can get if you divide four-dimensional hyperspace with these three-dimensional hyperplanes. And, you know, we might not be able to visualize it, but we can certainly fill in the chart here. What comes next here?
Well,
16,
oh, sorry,
which came from 8 plus 8.
sorry.
And then next would come 31. 1 less than a power of 2, just like this one was 1 less than a power of 2. And next would come 57. Nice. Okay. So as far as finding a formula, somebody mentioned something about Pascal's triangle. So don't tell. I want to give other people a chance to see if they can find these pizza numbers and watermelon numbers in Pascal's triangle. So if you already know this, give other people a chance. So are people familiar with Pascal's triangle? How am I getting one row of numbers from the previous number?
Just adding them
Okay, adding adjacent numbers gives me the next number. So the pizza numbers are not just sitting here in Pascal's triangle. You have to add a few numbers together to get those pizza numbers.
Oh, I see.
Okay, give other people a chance for a second. Raise your hand if you think you see where to find the pizza numbers.
Well, actually, I thought I did, and then I went farther, and that's not right anymore.
Oh, that's so cool.
Well, sometimes we start in math circle with actually 0 something. So you can start with 0 cuts, and then you get 1, 1, 1, 1, 1, 1. Because you cut it 0 times, cut it 0 times, cut it 0 times, you end up with 1, right? Because you got one pizza, one pizza, one pizza. So that 1, those 1s show up on the left side. You do no cuts, right? I mean, that's a strategy we use a lot of times in math circle. Instead of starting with 1 cut, you start with no cuts.
Yeah. Well, there are these zeros with ones alongside, but I'm not sure that that's from the 0
Okay, well, in other words,
cuts.
we don't,
Yeah.
suppose you got like a 0 dimension instead of
Okay.
1 dimension. So start with licorice with 1 dimension, start with a point.
Yeah.
You can't cut a point in half, can you? So you still have you always have 1 point.
Yeah. All right. So somebody who sees these pizza numbers, where are they? Yeah.
Like the sum of the first 3.
Okay. So yeah. So if I take the sum of like the first 3 in a row, so like right here, let me number the rows. So this is n equals 0, n equals 1, n equals 2, n equals 3, n equals 4. So for the pizza numbers in the 3rd row, say 1 plus 3 plus 3 is 7, and that's the 3rd pizza number. Okay, 1 plus 4 plus 6, 11, the 4th pizza number. And we're about the watermelon numbers.
So add the
Change.
Makes sense now.
So 1 plus 6 plus, 1 plus 4 plus 6 plus 4 is my 15, which is my fourth watermelon number. So if I number these entries, k equals 0, k equals 1, k equals 2, k equals 3, for those. Wait, yeah.
Yeah.
So the watermelon numbers here, so the watermelon numbers are the sum of the first, what did we say, 4 entries in row n. Okay, so that's a nice way to find a formula. If you're familiar with Pascal's Triangle and know how to write these numbers as binomial coefficients, that can give me a formula. So, for example, if I want to find, well, let's just say W of 5, that's going to be the sum of these first 4 entries in the row 5, so that's, in terms of binomial coefficients, this number here is 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, like that. And in general, if I want to find Wn, that's going to be, what?
N
N
choose
choose 0. In fact, it gives me a, I mean, where do you think you're going to find this hyper watermelon numbers? Just add another binomial coefficient to that. So, pretty amazing. Now we haven't proved this, right? This is just an observation. So, one of the problems on the problem sheet that I'll hand out asks you to prove this using mathematical induction, which is kind of a fun exercise also that uses your understanding of how Pascal's triangle works and how binomial coefficients add up.
So then 5 space, you just have to wait down a few rows and extend it to that.
Yeah, in fact, you don't even have to go down a few rows if you want to get the, if you wanted to get the, for 3 cuts in 5 space, you would like to add together, I guess, the first 6 binomial coefficients. Well, you sort of run out of space, but if you just add these and, leave the rest, add on zeros for the rest.
Because we were already doing that. Like,
Yeah, yeah.
I think there's a way we can bring the dimension down, dimensionally reduced by 2. And so if you want to get the hyperplane numbers with pizza, you draw a pizza and you put 3 points along the boundary of pizza. Now you connect those points with all possible lines. And joining, how many pieces do you get? Then you do the same thing with 4 points and connect with all possible lines. And now how many pieces do you get? And start looking at the pattern there. So that's pizza cutting, but look at the numbers.
But the numbers are giving you these
You could do the
numbers.
same thing with watermelon if you wanted to see 5 dimensions.
That's
The
pretty
dimension problem.
Alright,
Triples of points with planes going through in the watermelon.
so this also gives us a way to check our formula against the binomial.
Wait, those are, sorry, those are
those
not,
are the H ones.
those are watermelon numbers? Those are H numbers.
These are
So
H.
one number,
This
so
is
let's
those
try
are
it.
4-dimensional
So
numbers
here-
that I'm getting with the pizza. So I
Ah.
went down 2 dimensions.
4, 5, 6, 7, 8. So with 4 points, we're getting 8, and with a 5th point,
Wait, but then, that, 8 is the answer for 3 cuts, right? So it's n minus 1
yeah, it looks like
or whatever.
so once we call this? We should call this Dave's number n. So with n point, I'll call it Dave number p. So for p points. So I think what we're suggesting is that Dave's number for p in dimension 2 or something is the same thing as our hyperspace problem with p minus 1 cuts. That's what we're suggesting here. And the same thing for other dimensions.
Are you absolutely sure though? Because we just saw the one example.
It's what my intuition says.
Well, this is a problem that Paul told me about, actually.
Yeah,
Right? The
yeah.
problem that Dave is
These
doing.
numbers, Dave is right about that. I don't see it geometrically, but it's true combinatorially, or it's true because the recurrences work that way. It's true because of Pascal triangleology.
But there has to be a way to projectivize
There has to
that,
be, yeah.
geometrically.
But I don't know about you, but I have trouble projecting anything from the fourth dimension and being sure about it. I'd like to, but
Well, I mean,
but I'm just
the
not.
fourth dimension, really what you're doing is
You're better at this stuff than me, that's for sure.
you're just doing the second dimension twice to do the fourth dimension, right? So, I mean, I haven't really
Second
thinking through,
dimension.
obviously, but when you put a new point on, not only are you doing the analogy where you're putting on extra licorishes that are each divided into X number of pieces, but the number of licorishes that you're adding are 2 less than the number of points that you have. You know what I mean? So if you're just taking those two numbers and you're multiplying them, which will give you, or it's like throwing you down a couple dimensions because you're doing the first dimension. You're doing the first dimension twice. So then you're going from the second dimension to the fourth dimension. Right. No. Like sometimes when I show my kids, they ask me like, what does the fourth dimension look like? Because I draw, like distance and then area and then volume. And they want to see the fourth dimension, like 3 to the 4th power. And you just draw 3 to the 3rd power and then draw another one over here. And then you count them up. And then that's 3 to the 4th power.
So what you're saying is every new point is a connection to all the previous ones. So in a sense, is that PVN minus 1, the previous, projecting it out to another point.
So like what I'm saying is like when you, let's say you started with these 4 points.
Right.
And you did that thing where you're connecting all of them.
Right.
When you add this point, like what we're trying to do is like
Connected to all the previous ones.
analyze it from here, from this column to this column,
Right.
right? Because this is a 2-dimensional pizza,
Right.
we're getting 4-dimensional numbers because when you put this point on, you're not only adding like this new licorice that's divided into the cuts, but you're adding 2 new licorishes that are divided into the cuts. So you're just
Right.
kind of like taking that first example and multiplying it by 2. So then the 2 multiplication is what kind of throws you over to that side. A rough way to look at it. And then if I were to put another point on here, it would be 3 new licorishes, each divided into however many pieces. So that's kind of geometrically, I don't know.
I have handouts with problems, sort of tracing you through some of what we've done and suggesting for you to prove the formulas. And then towards the end, if you just like solving problems, I have more slicing and dicing problems, including a crescent shape, an example of a non-convex shape, and slicing that into as many pieces as you can, and various other sort of related problems, which I think are all really fun. And I'll be around tonight, so I can pass these.
Oh, good.
I don't need all of them. Pass these around. And I'll be around tonight to talk more about it. Want to?
I really like how you named the functions with the licorice, the pizza, and the watermelon.
Yeah, my son pointed out that the convenient thing is L is also line, and P is plane.
Right.
Well, and
W is
W.
something
But,
bigger and more complex.
Yeah.